All right, Haley, if you choose to watch this, we are going back to an example we were doing right when class ended last time, and it was planetary stuff. So could you look at that, Dan, and remind us what was on the y and x axis for the planetary example?
The y-axis was period, which was by
so
year.
Period is how long is their year once around the sun, and what was this?
Distance.
All right. And they had a weird unit. What was it, Dan?
AU.
All right. And 1 AU is the distance between the sun and the earth. All right. So when we looked at that data, it was curved. All right. So we're going to go in with LNs and do the LN of the period and the distance again. So how'd that work out for them? So Bree, what happened when they took the ln of the y value and left the AU alone?
It was still really curved.
It was curved the other way. It got worse. Is it going like this, Bree, if I remember? Okay. So then, Bree, what straightened it out?
They did the ln of x and y.
Right. All right. I think we got that far yesterday. So, I'll ask you a question. This is an intuitive question. If one ln doesn't straighten it out, does that mean 2 ln's will? Definitely not necessarily. You've got to check it or look at a graph. So it's not necessarily that you're going to find anything that straightens it out. And then you can't make predictions. So this is a good place to go. If one ln doesn't work, this is a good place to go, but it might not work. Did it work, Bree, on this one?
Yes.
Straightened it out?
Yep.
All right, let's go with it. So, Maddie, give me the least squares regression line that you think would match with this scenario. So is that question number 2 again?
I think it's on the back.
Where's question number?
It's on the very back of those.
All right, A. All right, A, put a star by. That's the one we're coming back to. So we're at B, where Maddie's going to look at the mini tab, look at the transformation we have found to straighten the data up and come up with the regression line. All right?
So it's ln of the period equals 0.0002544.
Wait a minute. All right.
And then plus 1.49986
9986. I
ln
remember this.
of the distance.
All right, ln of distance. All right, that's where we were exactly yesterday. So we got to that point and the bell rang. So we're ready to pick it up and go on. That is the answer to B. Any questions on where she got those numbers? And notice ln is on front of both of the variables. All right. Could you read C for us? Use the model from part B. Let's not read it. Look at part B, just part C. Read it to yourself. And we're gonna ignore that big number. We're just gonna use the 102.15 and plug it in. So pull out your calculators. Or is everyone? Except you, it's not working, is that right?
No, I thought my old one just wasn't working because the batteries were next. I had to use it.
So you had found it and you didn't even try it?
I used it like earlier this year, I thought.
Okay.
And so I thought it was just I put your batteries back in
Part
there.
C, we are going to make a prediction with Maddie's line. And the prediction is, we want to know how long is the period or the year for a planet that is 102 AUs, 102.15 to be exact, AUs away from the sun. So just plug in the number right here, 102.15. Somebody give me what you got when you get to ln of p equals.
I got that.
What do you got?
I got 153.211.
150, right before you exponentiated?
Yeah. I got 6.939.
I got 6.9.
I got 6.9.
6.9 what?
39.
All
What
right.
did you get, Bree?
I got 153.211.
I also got that. I got that too.
Did you guys do the LN
She said
This is before.
Yeah.
No, it's LN.
There's an LN.
yeah, but we're not. We haven't
Yeah,
like
but-
hit the LN.
Yeah,
yet.
she's asking for it before you do the LN.
Okay.
No, the second LN. No, there's two LNs.
There's
an
two
LN
LNs.
on the
I'm
left
talking
side.
about before we have to
Yeah, I got
exponentiate.
Oh.
So
Is that what you're looking for?
how do you do that?
Huh?
Yes.
All right, so now,
Here, you have to
while,
here.
while you were out, we have it all on video for you.
You put it in like
Morgan,
it is there.
to get rid of the ln, we exponentiate both sides to the base. Ln is base e, and we went all over that, so you'll be able to see it later. Morgan.
It's okay.
All right, so we get period equals e to the 6.94, and that turns out for me around 1,032. Anybody?
1,034.
All right, it's going to be close depending on what actual number you used here. So, so who was getting, Bree, you were getting a weird number?
They
here?
didn't use the LN on the distance.
They
Yeah,
did
they did.
it?
It says LN
They
distance.
did it? Okay.
No, we didn't.
Read it.
Okay, sorry.
Recalculate.
That's the only place I see
You
them.
have to follow the equation,
Don't
so.
listen.
All right, we can find the ln of a number on our calculator. Over here, we had the ln of a variable, and we had to undo it with exponentiation. So we ended up with predicting 1,033 years, and now we get to interpret that, looking at the residual chart there. Do you expect this prediction to be above or below, too high or too low? So I'll let you think about that for a minute. So look at the residual and quietly come up with your answer, and we'll bounce it off of one another. How many we get?
I'm not getting 6.94 when I do 0.0.
What'd you put in exactly?
0.000. Wait, I'm missing a zero. That still shouldn't.
That'll make a big difference if you were missing a zero.
Eh.
So tell me what you're typing in.
I don't
I do
understand.
parentheses
Now you want us
before
to
you do the
interpret
plus
it?
because it's gonna add and then you're gonna please because it's outside. You want to do what's in the parentheses first.
I don't understand how to interpret this chart. Yeah, I'm
How to read
confused.
it?
Yeah, because if our distance that we're given is 102,
Well, you see, this residual chart is doing the ln of the
so
distance.
it's really 6.94.
So-
Because where did we
I did
start?
like
So the
zero.
ln of the distance is right back here.
But that's still pretty far away. That's still pretty hard to make a
Yeah,
judgment.
well-
It could have gone back down.
All right, you can make that your conclusion if you want.
And that's fine. That's a fine
I'll
answer.
talk about it.
Wait.
4, 5, 6, where are we? Almost 7. All right. So,
LN.
since the ln of the distance, I backed this up before I exponentiated it. I noticed on my residual chart, they were doing the ln of the distance. They had not exponentiated the chart yet. So I'm going to look where I think 7 is going to appear. So the chart stopped at 4, so I have to add a 5, a 6, and a 7. So do I really know where these dots are going to be, above or below? If you had to answer yes or no, high or low,
There's no
where
way of
would you
knowing.
say?
I would say hi.
I would say high.
Wait, there's no way of knowing that.
Well,
though.
I
you
would
see a
say
pattern.
Look at the trend.
Okay, but the pattern could go right back down. like-
Right.
Guys, I
So,
got it. It's 6.9.
I agree. Because what's that called, Kevin, when we go out beyond the data?
Extrapolating.
Right. So,
Extrapolation.
I think an appropriate answer would be that this is an extrapolation and the data cannot be used to make predictions at that length. But the book says, assuming the residual dot is above the prediction line, then the prediction would, so they're assuming that it would keep going, but like you said, how do we really know?
Put those down there.
So, that is their answer. They're assuming it's going to be above. If it was above, the prediction line is right here. So our prediction is going to be too low.
So assuming that the residual.
Dot is above the prediction line, the prediction would be too low.
What's that?
So, but I like Shannon. That was my answer. So great minds, right?
Miss Powell,
Yeah.
when we're looking to try to guess where it will be, what's the number that we go to for the residual side?
We just look at what is on the axis that they're giving us.
I
So-
found
When you call yourself
the where the dot would be for distance,
Right.
but when we're going up to see our predicted, where do we go? For the
Yeah,
line?
that's what we're fighting about. Like, we kind of have to guess, because the book assumed it was going to stay up. But since it's going up and down, how do we know that for sure?
But
So
like,
Shannon's,
So
on the
you're
last one, we had a
yeah, we were more close though.
because it was
See,
like right next to each other.
because see, we were at 190. We
But
weren't like way down here.
But we were
So-
given a this value to look at.
This part of the screen.
We were looking at this 190. It was way down here.
you don't have a y
Yeah.
variable to look at in your prediction, do you?
Right.
Have you
Yeah.
tried charging it?
So we
No,
were
I
down
haven't.
here
tried
at
turning it off to the
190.
If it turns
So
on,
we were
then
looking up and down.
If
to
it
see
turns
where
on,
we
it
thought
doesn't need to be
would
charged.
And since
You-
it
the
was
screen's
going like
broken,
that,
it's
we
not
assumed the
displaying
next
it.
one was going to be below
What is a
the
tiny bit?
prediction line.
Tiny bit.
Yeah, like
Sometimes
it'll
it's-
say
So
something.
190
Sometimes
is where we
I
were
can do
looking.
math on the bottom.
So we had 160 was up here, 170 was here, 180 was here. So we're assuming 190 was still going to be below. Just looking at
You
the
don't
trend.
But
use
why
your
would we
answer for C.
But then why would we say that our guess was too high?
This is
I-
this is the regression line right here, and it's above what
Daniel.
it was above that.
This is your prediction line. So following the pattern, the next one would be down here probably. So your prediction line's too high.
No, you have to send
okay,
it to the
All right.
fix. I was like, no.
All right, other questions
Outline my thing.
on that?
That's literally.
All right, so I'd accept either answer for this. So you could say extrapolation, can't tell, or we could say assuming that the dots stay above the residual line here, axis, then we would say the prediction line was going to be too low. All right, now we have to go do the starred problems. Can someone find the first star and guide us back gently to the first star problem?
The first star problem happened on
What page of the handout?
page, like the front of the second page.
3.
The front of the second page.
So this was the first problem about the years. It was a 1970 problem.
You should show me that.
All right, so it is 1970. So the problem says a scatter plot of the natural log of the number of transistors. Is that it?
Yep.
That's the first one we start?
Yes, ma'am.
Okay. So if you notice, we've been skipping A or number 1 for the 3 problems that we've done. And they both, or all 3 ask, is this an exponential model or is it a power model? So I have to give you some training on that. I didn't want to hit you with that in the beginning. I'd rather you had the stat down, and now we'll go back and grab the math. So, all right. So let us do that.
The second packet, the second page. Front.
12.2, second page, transistor problem. All right.
Yeah.
Now you still have room on the very front of 12.2 to take notes. Am I right?
No.
No.
Yeah.
I have this corner up here.
Yeah, okay,
Is
that's
that
it.
enough?
Yeah. Watch. I'm going to have 2 columns, so give it enough, right, small enough. All right, so the first thing, there are 2 models. I've already introduced you to power model. Like when you're eating the pizza, y equals ax to the b. So remember I said if you had to calculate the area of the pizza you're eating, you would have area equals pi, variable r, because it could be a 6-inch, a 9-inch, a 10-inch squared. So we use power models all the time. They're not that complex. And then the one I haven't introduced is an exponential model. And all I'm doing is training you to get these kind of questions right, because they love this question. It's an easy question if you've been taught. So, ABX is the exponential model. So here, the A and the B are constants on both of these, just like you would expect. A and B are constants, X and Y are variables. So, this one, an example of this one would be y equals x squared is a very simple power model, whereas an exponential model is y equals 2 to the x. Do you remember graphing those in our good old pre-calc days?
Yes.
All right, this is called an exponential because the exponent was in, the variable was in the exponent. And this was the old smiler. So this one will go up quicker. They both stay the same for a while, and then this one goes shooting up a little quicker. But we don't really care about that. What we care about is how this fits into this straightening of data discussion. So for now, I'm just going to wax mathematical, and at the end, we'll be able to see how it fits in. So the first thing I'm going to do is I'm going to go back to this power model, and I'm going to take the ln of both sides. I can do a log as well. Take the log of both sides. On the right, you see there is a product, a times x to the b. So we reviewed the log rules before we got very far into this part of the chapter. So what can I do with two logs? With a log, I want to write two logs with, I have one log here with two factors. What do I do with them?
Separate them.
All right, with what?
An addition sign in the middle.
All right, so ln of a plus ln of x to the b. So we use log rules because logs rule. All right, so we have rewritten using log rules. When you have the log of two things multiplied, they can be written as two logs added. So, and what log rule can I apply now?
You can make the b into a root.
All right. Well, up here
Right.
here it's an exponent. Down here it's called a coefficient. But that's okay. Just bring it down in front. All right. So now I'm going to simplify. So ln of y. Now remember I told you a was, what was it, a constant or a variable?
Constant.
So ln of a is also a constant. So I'm going to just call it a c for a constant, c sub 1 in case there's another constant. And then I have b, b is a constant, I'll just call it another constant, ln of x. So I just got rid of the a and b and called them constants, so you can see how many logarithms are left very easily. So notice there's still two logarithms left. So note, two logs are left in this last statement.
I'm confused about the step where they changed into C's. Wait,
Just
what
to
happened?
indicate these are constants.
Okay.
Alright, so I have two ln's. Do you notice that there are two? 1, 2. ln of x did not disappear, ln of y did not disappear. They're still there. So, if you have your data straightened out by two logarithms, that means you started with power model. So, which example did we just do recently where we needed two logarithms to straighten out the data?
The population.
I don't think that was two.
The space one was.
Which one? Look
Planet
at
one?
Oh,
the
no,
planet one. Remember we had to take the ln of both the distance and the period. So if you end up using two logs to straighten out your data, so if two logs are used to straighten your data, you start it with a power model. Why does that matter? I don't know. It seems important to the stat powers that be. Because they'll say, what kind of model are you working with? Right in the middle of the problem. So that's the way you can tell. If you have two logs in your answer. So I'm assuming something's going to happen differently with the exponential side. So let's pull out the math and see. The exponential side, we're going to start down the same. I'll give you a second to catch up. If two logs are used to straighten your data, you start it with a power model. All right. You up to me?
Yep.
Exponential, ln of both sides. Let's see if you can work a step ahead of me. Just for fun, just for mathematical fun.
Is it 1 log?
All right, see if you can do the next step. Jumping in, similar to the one before, we have the ln of two things that are multiplied. So I'm going to split them up as I have the 1 log of two things multiplied. I'm going to change it to 2 logs that are added. So very similar to the concept that we just saw on the power side. So now, what rule is left? Once again, the exponent can run down in front. And now you can christen some things constants and some things that aren't constants. So see if you can figure out what is a constant now and what isn't.
Wait, why would it be different?
Because it is. There are different results. So here I got ln of A is a constant. Because A is a constant, the ln of a constant is also. Here I have an ln of B, which is that a constant? Ln of B, it is. So I'll put the x over on that side for good looks. So how many logs did I end up with when
Should
I
it be
started?
ln x? Or just x?
There's no ln x here. The x came down in front.
Oh, right, right.
LNB.
It was ln
Yeah,
B.
yeah.
So how many logs did I end up with?
Oh no.
All right, so if you use, or we'll say if 1 log is used to straighten your data, you start it with an exponential model.
Damn, so excited.
It's like gonna be a question like which model did you start with?
Yep. All right, so let's go back to the first one that we skipped and we put a star by it. And see what we can do with that answer now. All right, going back to the transistor problem, we put a star on A, question A. A scatter plot of the natural logs of the number of transistors on a computer chip versus years since 1970 is shown. Based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between number of transistors and years since 1970. So, can you find the answer floating around in front of you?
Yeah.
They gave you the answer, they said it's exponential, so what's a good way to answer that?
Because we only are using 1 log.
They only ln.
It only took 1 log on that problem to straighten our data, so
Yeah.
we know it came from an exponential
They only
model.
ln the transistors.
So we are out there counting our logs. If you look at the data there, we only used 1 log to straighten it. So therefore, we know it's an exponential model because it only took 1 log to straighten it out. All right, let's go flip over to the next one where we have a star, and that was the one you had to do for homework last night. And it's explain why it would be reasonable to use an exponential model to describe the relationship between blah and blah. So the answer is identical, because once again, we only used 1 log to straighten that data. So the exponential model is correct because we only used 1 log to straighten that data. You okay with that? All right, and then once you get that down, you can flip back to the one we skipped today, which was A on the planet problem. Explain why a power model, blah, blah, blah. So what's the answer
So it tells
to that one?
2 logs.
Right. A power model straightens data when 2 logs are required.
That's easy peasy.
Yeah. It's a little bit of memorization. If you don't want to go through this every day on your paper, you got to kind of study power matches 2 logs, exponential model matches 1 log. So a little bit of memorization, but that is why. All right, let me give you one to do where I'm not going to tell you what the data, how to straighten the data. So I'm going to give you the data, and you can try squaring it, cubing it, cube rooting the y values. You can try 1 log, you can try 2 logs. So just try different things on your calculator and see which straightens it out. So the first thing you want to do is put your data in and see maybe it's already straightened. Don't count on it.
This is for homework.
It's for right now.
Oh, okay. I have an extra copy for Haley. Thank you.
Alright. Alright. Putting, can you just read it to us, please, Dan?
Yeah.
Thank you.
Just start with A, or
So just the prop.
okay. Here are some data on the hearts of various mammals.
That's it, huh? Alright, so observe. What are they telling us in both columns there, Joel? We haven't heard from you. I've been trying to leave you alone.
No, you're fine. The first one is the heart weight in grams, and the second one is the length of cavity of left ventricle in
Okay.
centimeters.
I have heard, I think it's true, that every single problem this book presents has been a real study. So that is quite remarkable, that someone's studying all these strange things. All right, so number A, letter A, you're supposed to make a scatter plot. So the only thing, may I caution you, I did this whole problem and got the answer wrong. And I know, shocked. And because it all started at A. If I hadn't done it ahead of time, we all probably would have. It says make a scatter plot for predicting heart weight from length. And that's not the order they gave us the data. So they're asking
So
us.
length is L1.
So they're asking us to predict heart weight. So that would be over here, heart weight
Yeah.
from length. So what should be in our A column?
The length.
Right. So in fact, if you already put it in, you could you just have to remember that and tell the calculator the opposite. So normally we put L1 in here, we put the X values in L1, and we put the Y values in L2. If you want to switch it up, you're on your own. All right. So do you know, once you put the data in, can you review for me, Maddie, what buttons did we pick to look at the scatter plot?
Okay, so you go to second y equals, right?
Stat plot.
And then stat plot 1, and then I think it's just the first option.
Right, it's the first option. All right, so do we have to do liner? Do we have to do liner?
Yes.
No. Do you realize when we're doing regression like this, there's no preconditions. So this is not chi-squared.
It's not like a test.
Yeah, it's not. We're not making any inference.
My dot plot is not straight.
It's not straight. Can I see it?
Yeah, it only has a few dots on it.
It's only showing me a little bit, but it's
All right, we
definitely
need to get all of them in the. You should have
Morgan, I
1,
got
2,
that.
3, 4, 5, 6, 7 spots.
No, I got
Some of them are on the line.
Oh yeah, they're on the line.
Oh, you got them? All right, so it's
on the
definitely
bottom.
like going
Similar.
like this and then up. All right, so we're getting this kind of for a while and then up.
Wait.
Yeah.
Yeah. Wait. It looks
L1 and L2. Mine looks like Morgan's.
Oh yeah, mine looks like that.
Yes.
Like
Oh,
this.
Dan, yours
did
is a
you
little bit
switch your
different.
L1,
I
L2?
I didn't go to second y equals at all. I just graphed.
Oh. Well, yeah.
But I'll switch it now.
It would be at like L1, L4.
Yeah, Daniel, because mine on this, I'd already said like L4, L3. You had to make it.
So are you telling it the X value is L1? It should,
Yeah.
I think it
It's gotta
goes that
switch.
way.
We've always done it the other way, so it's
Now it looks
still
like
in
it.
that way. So
What do
They
you
did
mean?
I'm saying it's always for second
You
y
fixed it.
equals. We've always had x list be L1 and y list be L2.
Right. So why did you
It
switch
should be like that, but if you
Did you
did it
put them
for-
in opposite?
I just did. Is
Did you
Opposite
put in
the right
length L1?
He got it right. He
Well,
got
his
it.
X-
graph is wrong.
No, he fixed it.
well, I fixed the
I
graph.
put length in.
I switched them and then it's fixed the
Okay,
graph.
I gotcha. All right. Hard to see. All right.
the curve
All right, so let's do, now you're going to work on your own and figure out what transformation would straighten that data. So, some choices, so you could take L1 and square it, or you could take the square root of this, or you could cube this and take the cube root, or you could do the
I gotta make it
ln,
linear.
the ln
How do
of
you do
this, or you could do ln of both, you could take log of one, so you're kind of just messing for a
Bless you.
while.
Times
There's
two.
options in that.
Yeah, well, we went over them when we walked in, we did the 4 options.
They should be in there.
So,
L2, how do I say cube?
How do I like see what the graph looks like with that one squared?
you're gonna have to put another column and square everything. And then come back and tell it to graph. Bless you, L1, L3, or whatever, you put your square data in. Did you hear that was a good question? Did you hear that? How could I look at the
Ooh, I
graph
got it.
if I'm gonna square this? So you're gonna have to create a column where everything's squared. You can do that quickly. Remember how you can go up in the margin and just define like L3 as
Which one do we
L1
square?
squared? What?
Should we square the cavity ones? The ventricle ones?
Should
You gotta find out.
The length,
We.
the length ones, that's one option. I don't know if it's gonna
No.
work.
should we make a new column and square it? Because you can go back to the column that they're in and square them.
Yeah, but then if it's
I would
wrong, you lost
lose
your
them,
data.
Yeah.
No, you can just do the square root. I got them right there.
I mean, the
Okay.
squaring it
I
got
got
it
some
closer.
choices.
No, Daniel, it's
Okay.
cube root. It's gotta be not square
So
root.
I squared it and then
It
it's
can
square
be-
root.
It can be,
doesn't have
they
to
can
be bad.
try square.
Squaring it helps a little
Yeah, it's
bit.
not good.
Wait,
What was that?
How do you cube it?
Square root.
How do
You
you
go
cube
up
something?
into L3,
Of the
like up to
You
the,
Yeah.
square rooted
and
this
then
one.
you do L1 to the third.
wait,
I don't
I'm
know.
squaring it.
Let's make a
Compare it?
list of the
Oh, wait,
things
wait,
that
wait.
aren't working. So,
Squaring is not working.
ln of
Squaring is
y.
caring.
L1, she squared L1.
Swearing is caring.
ln of y does not work.
Ln
is
of
caring.
y, ln of L2 does not work. I call it, I guess some people are calling it different, so I will say x squared, no.
Care.
And then you said ln of y.
Wait, mine's very close now.
ln of both didn't work.
I cubed just the one. I cubed
Oh, that did not help at
L1.
all.
Let me see your ln of both.
That made it worse, actually.
This is
That's ln of, how did you get it to say that? Do that.
I set up L3 and L4. L3 was the ln of L2, and then L4 was the ln of
Oh,
L1.
Miss Powell, I got it.
I graphed it.
I got really close to getting a straight line.
Maybe
Here's
not.
mine.
This is just the
Did I do it?
L1 being cubed. So
Okay.
it's just y being cubed. No, x.
How come there's just 2 points?
No, they're on the line. There's like 5, but they're on this line.
They
I
are.
Like that.
I'm pretty sure that these are other points that just on this line.
Okay.
Like these little
They're
dots coming up.
squares. Those are your tick marks.
Oh,
So
okay.
you're-
Well, then why are only 2 coming up?
probably they're out of range. So,
Yeah, it didn't like
these
my
didn't
L.
stat, yeah.
I didn't like my LNs.
all
It
right.
wouldn't let me graph them.
All
Oh,
right.
mine is not linear, dang it. Not even
All right. Joel,
Wait, no,
go
this is no curve at all. Wait,
I
I'm goofy.
tried ln of y and ln of x, and I got a straight line, Joel.
Me and Jay got a straight line.
I didn't.
Can't not have a
With
straight
what?
line if you only have like 2 points.
All right, what's that one?
This is you cubed L1.
That's making it worse.
I cubed L2.
You only have
Yeah.
you only have 3 points.
Mine has 4.
All right, we need all of them.
have a curved line if you only have 3 points.
That's L6.
Yes, you can.
That's why I didn't.
Let's see.
Right.
There's
No,
1, 2, 3,
no.
Oh, I got it.
6, 7
Mrs.
points.
Pell, I messed up.
Okay.
I had it as L3
Wait,
and
it
L2.
Wait, what did you
All right,
do?
where's your point? Oh,
Shannon,
that's sweet.
What'd you do?
Can you make those marks more
I
visible?
Yeah, I
aligned
can.
both of them.
That's the worst
Make
kind
them
of
plus.
user. Yep.
All right,
It's
show
a straight line, but it's still
Haley.
going up.
No,
All
no,
right.
she's not looking for this. She just wants to make sure it's straight. Like.
Oh, it
here
can be
we
straight
go.
like that?
Yeah.
So what's
Oh.
that one?
I LN'd both.
LN both, it works.
There you go, Haley.
All right,
Okay.
take this one home and
Ellen
one
of
more,
both.
and that will be it as the bell just rang. All right, so
Bye, Haley.
finish that one for homework. We have discovered that ln of x and ln of y straightened it out. Please verify that to yourself on your calculator. Then you probably have another question to answer. You have to do a regression. And here's another one that's just like it.
Both of these are for homework.
Yeah, finish the one and then do
This is one and yeah.
What's your record against
All
Harvard?
right.
What's your record against Harvard?
So Morgan, do you want to talk with me about what you missed?
So I
Or you wanna watch
will
the
take
video?
the
poster
Every year we
tonight.
like one and one.
I feel like I pretty much understand what's happening.
Okay, that's
Well,
cool.
we're gonna get to this.
All right,
But-
Haley, are we off? Are we off till?
No, not yet.
All right, Haley, till we meet again. Come in soon.